So let's say now you wanted to take a higher product. So let's say you wanted to FOIL 1 plus I to the fifth power. Okay, so you know that foiling all of this out is kind of annoying, right? So there's something else that we can do. So this is what we call Timorous Theorem. Okay, so what Timorous Theorem says is that if you have a complex number and you're raising it to some power, all you have to do is take that power, raise it to the power of whatever your R value is, and then multiply the theta value by that power, which is really nice because you don't have to be foiling this over and over and over and over again. Okay, so let's go ahead and apply that. Let me just show you basically why that's true. So we're going to start off with z is equal to, whoops, let me go back. So z is equal to r and then cosine theta plus I sine theta. Okay, so basically, let's say you wanted to find what z squared was. So z squared is just basically going to be c times z multiplied together. And we know basically what that is based on the previous one. So based on the product, we just said that we're just going to multiply the r values together and then take the sum of the cosine of the theta value. So it's going to be theta plus theta, and then plus I sine theta plus theta. So notice here you're going to get r squared, and then here you're going to have the cosine of 2 theta plus the I sine of 2 theta. Okay. So what about if you wanted to get r cubed? Okay. I'm sorry, z cubed. So you can basically write this as z squared times z. Well, I already know what z squared is. Z squared was r squared. And then z was just this r. And then we're going to have cosine of 2 theta plus this 1 theta plus I sine of 2 theta plus this theta. So this r's are going to give me r cubed. And this is going to give me cosine of 3 theta plus I sine 3 theta. So you can kind of already see the pattern that whatever power I bring this to, that power is just going to be the power on the r value, and also that power is going to be multiplied by the theta value. So that's basically what Timorous theorem says. So if I were to keep doing this many, many different times, I'm going to end up getting that formula. Okay? So let's do a couple of examples. So let's say, for example, I wanted to use Timorous theorem to evaluate 1 plus I to the power of 5. So notice here that the first thing that we want to do is convert 1 plus I into polar form. So let's start off by finding what r is. So r is going to be the square root of 1 squared plus the coefficient in front of I is just 1. That's going to give me square root of 2. And then theta is going to be taking the inverse tangent of y over x, which is just going to be 1. Okay, that's going to give me pi over 4, 45 degrees. Okay. So, and we know that that's going to be correct because it's in quadrant 1. So basically your z value is going to be the square root of 2 cosine of 45 degrees plus I sine of 45 degrees, or cis of 45 degrees. So now what we want to do, we want to take it to the power of 5. So you're going to take z to the power of 5. So what we're going to do, we're going to take the square root of 2 and raise it to the power of 5. And then you're going to take the cosine, and then we're going to take this 5 and multiply it by the 45 degrees plus I sine of 5 and multiply this by the 45 degrees. Okay, so now we have the square root of 2 to the power of 5. And what that's going to give me, if I put that in the calculator, it's going to give me 4 square root of 2. Then you're going to have the cosine of 5 times 45 is just going to give me 225. Plus I sine of 225 degrees. Okay, so this guy is basically going to be, if I were to FOIL this 5 different times, this is going to be the solution. So if you wanted to know what that was in complex form, remember all you have to do is just put it into the calculator. So I'm going to just say cosine of 225, and that's going to give me just this negative square root of 2 over 2. And then and then take the sine of 225. That's also going to give me negative square root of 2 over 2. So when I FOIL this out, what am I going to get? So what is this? So this is going to go away. There's going to be a 2. There's a negative there. Square root of 2 times square root of 2 gives me square root of 4. So it's just going to be another 2. And this should be a negative again, because there's a negative right there. So now you're going to have another 2 in there. And then you're going to have another 2 in there. So you're going to get negative 4 minus 4i. I hope I did this right. Okay, so that's basically what you're going to end up getting if I FOIL this 5 different times. Okay, so that's kind of how you use Timorous theorem. Okay, so another application to kind of end this section of polar is basically you can find roots. We know from algebra that z to the n equals w has n roots. And if you didn't, well, now you know. So, and you'll actually know this in pre-calculus. Basically, if you have a degree n polynomial, you have n solutions. So if that means if you have a third degree polynomial, a second degree polynomial, which we kind of know as a quadratic formula in this quadratic equation, if we have a degree 2, then you are almost guaranteed 2 solutions. Okay, they can be complex or they can be real solutions or repeated solutions. So that's basically what it says. So I gave you here an example. X squared equals 9 gives you 2 solutions. X equals negative 3 and x equals 3. So what we're going to do is we're going to extend this thing to, let's say, what happens if I raise a complex number to a power with a rational exponent. So what that basically means is, let's say you wanted to have z to the 1/3 or z to the 1/2 or z to the 1/7. So how would you do something like that? This is kind of like an extension of Timorous theorem. So it's called the Nth Root Theorem. And basically what it says, it's basically the same as Timorous theorem. So you're going to take the exponent, you're going to put that exponent on the r, you're going to multiply 1 over n, which is going to be the exponent by the theta, but you're also going to have this extra term. So, and this extra term is going to be this 2 pi k over n stuff. And that's basically gives you periodic roots. So because what you're really solving for is all the different solutions. So you're not only going to have one solution, you're going to have multiple solutions. Okay, so here is given to you in radians, okay? But of course, you can have it in degrees. I don't know where I can write it. Maybe I can write it over here. If you wanted it in degrees, it will be r to the 1 over n cosine theta over n plus 360 k over n plus I sine theta over n plus 360k over n. So basically what I'm doing is I'm substituting the 2 pi with the 360. So this will be in degrees. So just in case something is given to you in degrees, you can use this formula, which is basically the same. We just have 360 there. So the only key thing to kind of know is about the k value. K goes from 0 all the way to n minus 1. So for example, if this value of n was equal to 4, then the value of k is going to go from 0, then 1, 2, 3, and then you're done. Because it's n minus 1. So you subtract 1 off it because we're starting at 0. So it's kind of how we were solving solutions, but we're just stopping. It tells us actually when to stop. So this formula looks really, really confusing, I know, but it's basically just Timorous theorem. So we're going to just do an example so that I can show you what it is. So we have 2 examples to finish up this chapter. So here we want to find the cubed root of z when z is equal to 27 cis 240 degrees. So here, since we have degrees, it will be better to use this formula with the 360 degrees. So remember that the cubed root is basically this, okay, which essentially is z to the 1/3. Okay, so that's what we're going to do. So I know what z is. It's already given to us in polar form. So z to the 1/3 is going to be equal to, so basically what we're doing is we're taking our r value, 27, bringing it to the 1/3 power, and then we're going to write cosine So it's theta, in this case, is 240. We're going to divide this by 3 because n is 3. Plus, we're going to write 360 k over n, which is 3. And then plus I sine theta, which is going to be 240 over 3 plus 360 k over 3. Okay, so let me clean this up. So this guy's just going to give me 3. This is cosine, so 240. So we're going to have 240 divided by 3. That gives me 80. Plus 360 divided by 3. That's going to give me 120. K. Plus I sine of 80 plus 120k. So this is not the answer. I'm just going to circle it because now what we have to do is we have to look at all the individual roots. So now we're going to start off with k equals 0 because that's our starting point. Okay, so 0 is going to be our starting point. What's going to be our ending point? Well, since n equals 3, then we are looking for n minus 1. That's going to be 3 minus 1, which is 2. So we're going to stop at 2. Okay, so first let's start off with 0. So I'm going to have 3 cosine of 80 plus 120 times 0 plus I sine 80 plus 120 times 0. Okay, so you can see that that's going to go away. So all we're left with is just 3 cosine of 80 plus I sine of 80. So that's basically the closed form, or how I would say the exact solution. If you want to know exactly what that is, all we got to do is just plug it into the calculator. So cosine of 80 is just 0.17 plus I sine of 80 is going to be equal to 0.98. Okay, so you can multiply this out if you want. So 3 times 0.17 is going to be 0.51 plus, and then 0.98 times 3 is going to give me 2.94 I. Okay, so that's the one solution. Okay, so now we're going to go to k equals 1. So now what we're going to do is we're going to plug in 1. So we're going to have cosine of 80 plus, now this is going to be 120 plus I sine of 80 plus 120. So you're going to have the cosine of 120 plus 80. That's going to give me 200. So the cosine of 200 plus I sine of 200. Okay. So you're going to have the cosine of 200. That's going to give me a negative 0.94 plus the sine of 200, which is going to give me a negative 0.34 I. And then, of course, you can always just FOIL this out. So this is going to give me negative 2.82 minus 0.34 times 3, 1.02 I. So that's going to be that guy. And now finally, we're going to do the last one, which is k equals 2. So you're going to have 3 cosine of 80 plus 120 times 2. So 120 times 2 is going to give me 240. Adding 80, that's going to give me 320. So plus I sine of 320. So let me just put this in the calculator. The cosine of 320 is going to give me 0.766 plus I. The sine of 320 is going to give me negative, let me write this as a negative 0.64. Okay, so 3 times 0.766 is going to give me, let me write it down here, 2.298 minus 3 times 0.64, that's going to give me negative 1.92 I. Okay, so these are the three solutions. Notice that we don't continue on because basically what's going to happen is that you're going to go back to the coterminal angle. So you're going to go back to the originals. So if you kind of see this pictorially, basically what's going on is you're looking at all the roots. One of the roots seems to be in the first quadrant right there. The other one seems to be in the third quadrant right there. And the other one seems to be in the fourth quadrant right there. So basically what happens when I go, so this is k equals 0, k equals 1, k equals 2. If I were to go to k equals 3, it will go back to this one. That's where we would stop at that particular point. So these are basically what the cubed root is. So if you think about it, this is basically finding all the roots of the three different roots. Okay, so it's the cubes. Okay, so you had to have three different solutions. Okay, so now let's do this last problem. So find the three solutions to z cubed equals 8. Let's start off by writing it down. So c cubed equals h. And let's try to find the polar form of h. Well, if you think of h, what would be the r value? Well, the r value in this case will be the square root of 8 squared. And notice that there's no imaginary parts, which is going to be 0 squared. It's going to be square root of 8 squared, which is just basically 8. Okay, so that's what that is. And then theta, that's just going to be the inverse tangent of it'll be 0 over 8, because that's the y over the x, which is basically going to be the inverse tangent of 0, which in this case is 0. And that kind of makes sense because if you think about 8 is on the real part. Notice that there's no angle, so it's going to be theta equals 0. So you're going to have z cubed is equal to this r, so r is going to be 8. Then you're going to have the cosine of 0, let's just write it degrees, plus I sine of 0 degrees. Okay, now notice here we have it cubed. Now basically what we want to do is find the cubed root of this. Okay, so remember that if you want to find the cubed root, then all you have to do is just take the cubed root of this guy. So if you wanted to find the cubed root of that, let me just write it as z. If you wanted to find the cubed root, I guess we can write it like this, to the 1/3. Okay, so then it's a to the 1/3, and basically this whole thing is also going to be to the 1/3 power. To the 1/3. So remember that when we were trying to do this to the 1/3 power, what we did was that we had the cosine of 0 over 3 plus, since we're doing degrees, 360k divided by 3. Plus the I sine of 0 over 3 plus 360k over 3. Okay, so that's basically what we were doing. So let me just write this a little bit nicer. So it'll be a to the 1/3. So if we do a to the power of 1/3, that's going to give me 2. The first guy is going to be 0. Okay, so that goes away. So all I'm left with is just 360 divided by 3, which is going to be 120. So it's going to be 120k. Okay, because this is going to go away. And then plus I sine of 120k. So now all we want to do to find the three solutions is plug in all the different values. Now since n was equal to 3, that means n minus 1 is going to be equal to 2. So let's start off with k equals 0. So when k equals 0, you're going to have 2 times cosine of 0 plus I sine of 0. So notice at 0, this goes away because when I plug in k for 0, you're going to get 0. So this goes away, so you're just left with 2 times 1, which gives me 2. Okay, and that kind of makes sense because 2 cubed is equal to 8. All right, now let's find the other root. So when k equals 1, so 2 times the cosine, this is just going to be of 120, plus I times sine of 120. Okay, so you're going to have 2, and then you're going to have the cosine of 120 degrees. That's going to give me negative 1/2. And then you're going to take the sine of 120. That's going to give me square root of 3 over 2. So I square root of 3 over 2. So when I FOIL that, I'm going to get negative 1 plus I square root of 3. So basically what that means is that if I were to take this and cube it, you're going to get 8. And then finally, we're going to write k equals 2. So you're going to have 2 times cosine. So I'm going to take 120 and multiply it by 2. That's going to give me 240. plus I sine of 240. So you're going to take the cosine of 240 degrees. That gives me negative 1/2. And then you're going to take the sine of 240 degrees. That's going to give me negative square root of 3 over 2. Let me make this a negative. Negative square root of 3 over 2. So when I FOIL that, you're going to get negative 1 minus I square root of 3. So that means that if I put this guy in here, you're going to get equal to 8, and I cube it. All right, so this is it's a really good way to kind of do it. There's a lot of clearly, if I just took the cubed root, I wouldn't be able to get all these complex solutions. And when you get to pre-calc, you'll be able to learn about the fundamental theorem of algebra. But this is basically how you would do a problem like this.